Hello, grade 12s once again. How are you? This is Patrick Kamala taking you in a video 2 about momentum and the impulse, grade 12 in this year 2025. So we're talking about the conservation of linear momentum in the video 2. If you enjoyed the video 1, this is video 2 following momentum and the impulse. So we're looking at the conservation of linear momentum. This is video 2. Okay. Now, for more information about extra classes, you can call us on 0785 We're starting now. Why not? Conservation of linear momentum. Now, conservation of linear momentum, how do we state it? The total linear momentum of an isolated system remains constant. If they say state the law of conservation of linear momentum, so what? You say that the total linear momentum, okay, you see, the total linear momentum of an isolated system remains what? Remains constant. That's how we state it. Now, if we don't want to use these words here, this is how we say it in our formula. So that the total momentum, okay, that means summation of the momentum initially, okay, equals the total. This sum means total of the momentum after. Okay, that's why we say here it is P final. Okay. Note that here the objects are colliding. So we are going to have object A and B. That is a momentum of A before plus momentum of B before equals total momentum of A after plus momentum of B after. So this is before for both of them. Then we add, then later we are gonna equate to the sum of the momenta after. Or we can say MA VI A plus MB V initial B equals to mass of A times V final A plus mass of B times V final for B and so on. Okay, let us see how we apply this in our questions. But we have the terms to define here. What is a system? We mean a certain number of objects and their interactions with each other. What about external forces? The forces outside of the system. What about system which is isolated? We said it's a system on which the net external force is 0. Okay, here we go. Now, Newton's third law and the momentum. So during a collision, the objects involved will exert force on each other. The forces according to Newton's third law, so that if object A, hope you remember this, we said that what? If object A exerts a force on object B, what happens? Object B will exert a force of object A, where the two forces are equal in magnitude, but what? But opposite in direction. Okay. Now, understand that the magnitude of the force, the contact time, and therefore the impulse on both objects are equal in magnitude. Okay. Now, when we have this one happening, we have got two types here. We classify them as collisions and explosions. Collisions and explosions. So under collisions, we have got three types. Okay, where objects move off together. That's number one. Where objects move off together. Number one. Then number two, where they collide and deflect. Okay. And then number three, where objects drop vertically on the moving object. Likewise, even under explosion, we have to call as explosions. Number one. Then for springs, number two, and the firearms, number three. So in your exam, expect any of the six here to come to you. We are going to look at them in detail, and we are starting straight away. So here we go. Now we start with the collisions where they're going to move off. Now in this particular case, when objects collide and they move off together, their masses can be added as one object. Like after colliding, like this one was at rest because of V at B is 0 and VA is not 0. So the mass of A collides with B. Then after collision, they stick together. So in our calculation, we say that total momentum before equals total momentum after. But because they're sticking together, we're going to say MA plus MB times V final. because they are stuck together, they should have the same speed, né? But here we have ma times via plus mb times vib. Then that's what we do in our calculations. Please note that if they are stationary, then initial velocity is 0. We are going to see them in the calculations, don't worry about that. Then sometimes they can collide and rebound. So they can collide and move off separately. For example, this is object mass A, mass B. A is moving to the right. What about B to the left? So they collide here. When they collide here, then you can see that our A goes to the left. What about B? Goes to the right. So that's when they collide and then move off separately. Now remember that the velocity and momentum, they are vectors, so it must be direction specific when we're doing our substitution. Okay, note that by the conservation of the momentum, we said that total momentum before collision equals what? Total momentum after collision. So the formula applies. Sometimes we use, actually I prefer using in most cases we use m1 v1 initial, okay, then we say plus m2, okay, v2 initial, if there are only two, equals to m1 v1 final plus m2, okay, and then v2 final. So depending on the given information, we can substitute and then calculate whatever they want. But don't forget that velocity and momentum, you must choose direction and then answer accordingly. Let's look at an example here. This was asked last year, 2024, from Eastern Cape, question 4. They said here that a delivery vehicle, okay, you can see it here, guys. They said that a delivery vehicle of mass 5,000 kilograms moving at a velocity of 15 meters per second to the right collides head-on with a car of mass 2,000 moving at 20 meters per second in the opposite direction. Immediately after the collision, the car moves at a velocity of 5 meters per second to the right. I repeat, a delivery vehicle of mass 5,000 kilograms moving at a velocity of 15 meters per second to the right collides head-on with a car of mass 2,000 moving at what? At 20 meters per second. You can see it here, opposite direction, okay? Then immediately after the collision, the car moves at a velocity of 5 meters per second to the right. So this is the delivery van here colliding with this car. Then after collision, this car moves to the right. What about initially? It was moving to the left, okay? So they said that I write down the principle of conservation of linear momentum in words. What did we say? That the total linear momentum in an isolated system is conserved. Okay. Then 4.3 is that calculate the magnitude of the velocity of the delivery vehicle immediately after the collision. Now we have got two masses here. We have two masses here, and so here we go. So what do we know? Doing 4.2, know that the total momentum, okay, initial is equal to total momentum after, we could find it here. So in other words, you can say the mass of the first vehicle, that's m1, okay, v1 initial plus m2, okay, v2 initial should give us m1 v1 final plus m2, okay, then v2 final. Now we can choose east as positive, né? So if we choose east as positive, it means that west is going to be negative, né? So the mass m1 that we know it is 5,000, né? So you're going to say 5 what? 5,000, okay. We say 5,000. It's not erasing, né? Okay. On space here, okay. So I'm going to say that the mass for the van, okay, what you like this, it is 5,000 kilograms, okay. What about initial velocity for the vent is positive 15 because it's pointing to the east, né? That's positive 15 here, okay. Then plus, now the mass for this car is 2,000, that's 2,000 here, 2000. As you can see, it's going to the left, it's going to be negative here. That's negative 20. Okay, should give us the one for the now after collision. Remember looking for the velocity after of the van immediate after collision. Okay, we're looking for this V2 final. So this must give us need some space here. All right. Okay. Equals to mass of the van. Okay, that is 5,000 altogether. Sorry, times mass of the van actually final. That's what I'm looking for. And plus mass of the car, which was what? So looking for V1 final. Here they gave us 2,000 for the car, for the small car here. What about its final velocity? They gave us 5. I think you can see it is 5 here. 5 meters per second. Okay, so this is positive 5 here. Positive 5 here. Alright, calculators now. Let's check it out. What do we get? Calculator, what do we get here? Okay, so that's it. I've got 5,000. Okay, I have 5,000 multiplied by 15, and then plus open bracket 2,000. Okay, 2,000 multiplied by negative 20, which gives us what? Negative 35,000. I mean 35,000 positively. 35,000 here. 35,000 equals to, this is 10,000 here. 10,000, 10 plus 5,000, and then we final. Okay, so here now 35,000 minus 10,000, what do we get? We get 25,000. Okay, we get what? 25,000. So 25,000 equals to 5,000. Okay, times V final. Also divide by 5,000. Divided by 5,000. Okay, so what do we get here? We're going to get RV final as what? As 5. So it is 5 meters per second. 5 meters per second. So what must we do? Do they want magnitude or direction? Let's check it again. They said that magnitude, so it must be 5 meters per second. Now they said that if the collision lasts for 0.4 seconds, calculate the force the delivery vehicle exerts on the car during the collision. So we want the force of the vehicle on the car. Now I'm going to use F net equals changing momentum or changing time. So we can use our F net. We can use F net, okay, equals to change in momentum divided by change in time. We're talking about the car now. We're going to say that force equals to mass. Now V final for the car minus V initial for the car divided by change in time. Okay. Now the mass for the car we know it is 2,000. Okay, 2,000. What about final velocity? They gave us 5. Okay. What about initial? Remember this car was going to the west. Let's check it again. Yeah, that is 20, negative 20. So minus 20, minus 20 here, divided by change in time. Do we know the change in time? 0.4 seconds. So here we have 0.4 seconds. 0.4 seconds here. 0.4 seconds. So we can start we get here. Let's check it out. Let's check it out here. So this time we have 2000, okay, multiplied by, open bracket, this is actually 25, ne? Then divided by 0.4. It gives us 125,000. 1, 2, 5. That's our force. That's our force by the vane on the car. Okay. All right. Next. Now we can also have object dropped vertically on a moving object. For example, a stuntman jumps off a bridge and lands on a track. Now, note that a linear momentum means momentum in along one axis. Ne? So this person jumping off from the bridge going to the car, the velocity of that person is going to be 0. We're saying that a dropped object has a horizontal velocity of 0. That's why this V here is 0. We're going to see it in one of the examples. Now, in that case, our equation, you're going to have it as the momentum before equal momentum after. Now, we're going to have MA times IA plus MB times IB equals to MA plus MB times V final. Because now the person is going to be stuck on that car, on that second object. That's why we are adding the masses together here. And I hope we are together. Now, let's talk about explosions here. Objects that experience the same explosion will experience the same force. I repeat, objects that experience the same explosion will experience the same force. The acceleration, velocity, and the momentum of objects is dependent on the mass. And objects that are stationary, they have initial velocity of 0. Okay. Now you see here, this now explosion with something to explode mean that they were together at first. Ne? They were together at first. Ne? So they can be together when they are at rest or when they're in motion. Okay. Now, if they are together, the mass of A and B must be added. That's why you're saying MA plus MB with the initial velocity here. Then after explosion, now they separate. As you can say, A is going to the left. What about B to the right here? Then now we can do substitute and do our calculations. Let's have an example here for this matter. This was done in Limpopo last year 2024 trial. Let's work it out here together. Perhaps it will make more sense to us. Let's say that a ball is falling freely. When its downward speed reaches 9.2 meters per second, it explodes into two equal parts. Part 1 goes straight up to a height of 13.7 meters above the point of explosion. So at first the ball was just a ball. Then that's before explosion. Now at a certain height, now it explodes into two equal parts, M1 and M2. Okay. Then what happens then? They say that defining what the term momentum was applied to physics. What is momentum? We said momentum is the product of the mass and velocity of an object. Then they say what must we do next? Calculate the initial velocity of part one just after the explosion. Calculate what? Initial velocity of part 1 just after the explosion. Okay, I repeat the question. They say that a ball is falling freely. When its downward speed reaches this one here, it explodes into two equal parts. Part 1 goes straight up to a height of 13.7 meters above the point of explosion. So looking for the velocity of part 1 initially. It's equal to the initial velocity of part 1 just after the explosion. Okay, so let's see what we have here. Now, first of all, the parts C are equal, meaning that the two masses, M1 is equal to m2, okay, which I'm going to call m. Okay, now because it was falling freely, it must be a projectile. Okay, so it goes straight up to this height here, 13.7 meters per second. So I can choose down as positive. If I choose down as positive in projectiles, it means my gravity is what? Is positive 9.8. Okay, meters per second squared. Okay, so now because it goes to maximum height, I'm looking for the V initial. So I'm gonna use V final squared, okay, equals to V initial squared plus 2a change in y for mass 1. So now at maximum height, velocity is 0. I'm gonna say 0 squared here, 0 squared. I'm looking for this V initial, V initial squared plus 2a. My acceleration is positive 9.8, okay. Now because I chose down as positive and the part 1 was going straight up, it means that the change in displacement is going to be what? Negative. So must be negative what? Negative 13.7. Okay. So from here, what's my V initial? If I find the square root, okay. So being a negative, it's going to be multiplied and taken become positive that side. After multiplying it 2 times 9.8 times that one, 13.5 under root. Okay, so I'm going to say here that square root of 2 multiplied by 9.8 also multiplied by 13.5. Okay, it gives me 16.266. I can say 16.27. Okay, so this is 16.27, 16.27 meters per second. Now I notice upward, because it was going up initially. Okay, then they said that they wanted the velocity, so I must say this meters per second upwards. Now even though I chose downwards as positive, but we know whenever you take a square root, you get two answers, the positive and the negative. So here I must make it negative, then I say afterwards I say upwards. So I hope we are together. Now they say state the principle of conservation of linear momentum in words. The total linear momentum in any isolated system is conserved. Then 4.4, calculate the magnitude of the velocity of part 2 just after the explosion. Okay, now when they explode, now I'm gonna use now linear momentum conservation because they are all in vertical motion. Okay, they are in vertical, so I'm gonna use now. Remember, at first they were together, so if I'm going to use the law of linear momentum conservation, I'm going to do like this now. I'm gonna say that the total linear momentum before collision, okay, the total momentum before collision equals total momentum after collision. So that means final, meaning that the m1, okay, the m1, which was together with the m2, remember they were combined, and we are moving together at the same velocity, the initial, because the ball was not yet split, equals to m1, okay, u1 final plus m2 v2 final, so we said the m1 equals to m2, which is m here, right? You can see that here. So I'm gonna say m plus m, which is 2m, okay, 2m. What about was our v initial? They gave us let's take it 9, what? Let's take it here 9.2 meters per second, 9.2 meters per second. Remember that's what it was going down. Okay, so that is positive 9,2, 9,2 equals to m1, which is m. Okay, now this v final, why not? This is m1. That's what went up, ne? They said that that's what I calculated here actually. That is the 16,27 now. 16,27. So this is 16,27. Okay. Remember it was going up, ne? Must be made negative now because I chose down as positive. Okay, then plus now the m2 is also m. I'm looking for this v2 final. V2 final. Okay, so here now 2 times 9,2. What do you get, guys? 2 times 9,2. 2 times 9,2. Yeah, it gives me 18,4 m. 18,4 m equals to negative 16,27 m. Okay, 27 m. Then plus m times v2 final. V2 final. Okay. So here I can divide through by m, ne? Or I can bring this 16 to the positive. So it can be 18 plus what? 18,4 m plus 16,27 m equals to m v2 final. Okay, so what's 18,4 plus 16,27? 18,4 plus 16,27 plus 16,27. So it gives us what here? It gives us 34,67. 34,67. So this is 34,67 m equals to m v2. So divided by m now. Divided by m. So up to the m cancelling here. I have my v2 final as what? As positive 30 what? 34,67 meters per second. Meters per second. Remember it was going downwards, this mass too. So that's our answer there. It's 34,67 meters per second. Okay. I hope we are together. Hope we are together. All right. That was just after collision, okay? Because they said they wanted the magnitude, so not talking about direction here because they want magnitude here. Now sometimes we have springs. We have springs, and this is what happens to the springs here in our explosions. Now springs here. The spring will exert the same force on both objects at Newton's third law. The acceleration, velocity, and momentum will depend on the mass of the object. So it's gonna be 0 if it is stationary. Okay. Now these two, they are stationary here with the spring in between. So when they are released, we say that when they are pushed, the mass are gonna go separately the opposite directions. Now, as you see here, A to the left and B to the right here. Again, we use the same formula. We say total momentum before equals total momentum after. Then we substitute and do our calculations. Don't forget momentum and velocity. They are what? Direction specific. Now this question came last year, 2024 May, June. I think we can write here. They said that two trolleys A and B of masses 3,2 kg and 2,6 kg respectively are held at rest on a horizontal frictionless track with a compressed spring between them as shown in the diagram below. The spring here, this is A and B here. After the trolleys are released, the spring extends its natural length and then falls onto the track. Trolley A now moves with a constant velocity of 0.4 meters per second to the left. What about trolley B? Moves with a constant unknown velocity to the right. Then trolley B reaches the end of the track after 1.3 seconds. Okay, I repeat here, I repeat the question. They said that two trolleys A and B of mass 3.2 kg and 2.6 kg respectively are held at rest on a straight horizontal frictionless track with a compressed spring between them as shown in this diagram here. You can see that. Then they say, after the trolleys are released, the spring extends to its natural length and then falls onto the track. Trolley A now moves with a constant velocity of 0.4 meters per second to the left, while B moves with a constant unknown velocity to the right. Okay, this B is going to the right. Then trolley B reaches what? The end of the track after 1.3 seconds. So what do we calculate? They say that state the principle of conservation of linear momentum in the words. So what do we say? We say that the total linear momentum in any isolated system is conserved. Okay. Then 4.2. Calculate the distance traveled by trolley B in 1.3 seconds. So we want distance by trolley B in 1.3 seconds. So that's what we're looking for here in 1.3 seconds. Okay, so now to get our distance, because the set is constant, moves with constant unknown velocity, and we're looking for the distance. Okay, distance. So what do we know about distance? That distance, okay, equals to velocity times change in time. Ne? So if we can find the velocity and we know the change in time as 1.3 seconds, then we can just multiply it to find what we are looking for in this case. Ne? So at first they were together, you see they were all stuck together with the spring. So we say total momentum initial equals to total momentum final. Ne? Okay, so because they were all together, as you can see them here, they were stationary. Ne? So we're gonna say that combining the masses. Ne? I'm gonna say M1 or MA plus M2 all together, having the same V initial all together, equals to M1 V1 initial, final, plus M2, okay, then V2 final. Now the masses I know here, 3.2 and 2.6, okay, 3.2 and 2.6. So here we have 3.2 and 2.6. So 3.2 and 2.6 here, but they were all at rest. So times 0 altogether equals to M1, that is 3.2. Now if I choose the east as positive, I'm going to make this one be negative. You see it is going to the west, 0.4 but negative, 0.4 but negative, okay, then plus the 2.6, which is this other mass here, 2.6, yes, 2.6, 2.6. I'm looking for its velocity, so I'm going to call it V2 final. Okay, so I'm with my calculator. This side is going to be 0 actually. So here I'm going to have 0. What about here? 3.2 times 0.4. 3.2 times 0.4. I have 1,28. So this is 1,28, negative 1,28, 1,28, then plus what? Plus 2,6 V2 final. So now the negative becomes positive, né? So 1,28 equals to 2,6 V2 final. So divided by 2,6 to give us our V2 final. So 1,28 divided by 2,6, what do we get? Calculators again. 1, what? We are saying here 1,28, 1,28 divided by 2,6, 2,6. It gives us here 0,49, 0,49, 0,49. Now this is the speed, né? Remember the question was asking for the distance, né? So our distance traveled by that other trolley equals to speed times change in time, né? So the speed is 0,49. The speed time was how much? 1,3 seconds. So times 1,3. So which answer do we get here? 0,49 times 1,3 times 1,3, 1,3, which gives us here 0,64. So it traveled 0,64 meters, 0,64 meters. I hope you guys were together here. Anything else they want here? They said that that's for distance. They said that the average force exerted by the extended spring on each trolley while they were in contact with the spring is 4,2. Calculate the time it took for the spring to extend to its natural length. I repeat, the average force exerted by the extended spring on each trolley while they were in contact with the spring was what? Was 4,2. They say calculate the time it took for the spring to extend to its natural length. No problem. So because we know the velocity now, we know the velocity. This one here, I think we can use this 0,4. We're looking for the change in time, né? So we can use our F net equals to change in momentum divided by change in time. Okay. Now the force given is 4,2. You can see it is here. That is 4,2. So you can see here 4,2 equals to the mass. I'm using this add-on here. This one, which is 3,2. That is 3,2 because I know the same as saying mass into V final minus what? Minus V initial, né? Divided by change in time. So the mass is 3,2. I'm going to put 3,2 here. What about V final? Now the V final here, I know it is 0,4. Okay. So negative 0,4 minus 0 because it was initially at rest divided by change in time. So my change in time cannot be negative, so I will have to make it positive. I'm going to say 3,2 multiplied by 0,4 divided by 4,2. So how many seconds were those ones? Let's find out here as well. So if we check our calculator here, we have 3,2 multiplied by 0,4 divided by 4,2 by 4,2 here, which gives us what? 0,3 seconds. 0,3 seconds. That's our answer. 0,3 seconds. All right. I think we have to stop here, guys. Then lastly here, they said that trolley B is now replaced by trolley C, which has a larger mass. The same compressed spring is placed between trolleys A and C. The trolleys are then released. The average force exerted by the extended spring on the trolleys remains 4,2 for the same period of time as calculated in question 4.3. How does the magnitude of the velocity of trolley C compare to the magnitude of velocity of trolley B after the spring has fallen to the track? Write only greater than, less than, or equals to explain the answer. I repeat, trolley B is now replaced by trolley C, which has a larger mass. Did you see that? The mass of C is larger than that of B. Ne? The mass of what? Of C bigger than the mass of B. And then they said that yes, they said that the same compressed spring is pressed between the trolleys A and C. Then they said that the trolleys are then released. The average force exerted by the average force exerted by the extended spring on the trolleys remains what? 4,2 for the same period of time. Okay. As calculated above, they say how does the magnitude of the velocity of trolley C compare to the magnitude of velocity of trolley B after the spring has fallen to the track? So, want the velocity of trolley C compared to velocity of trolley what? Of trolley B after the spring has fallen. Now, because of the larger mass here, because of the bigger mass, know that the velocity of trolley C will be less than velocity of trolley B. Why? What do we know? From Newton's second law of motion, when the net force acts on the body, what happens? The body will do what? Will accelerate in what direction of the net force? The acceleration is what? Directly proportional to the net force and inversely proportional to the what? To the mass. So, the bigger the mass, the smaller the acceleration and hence the smaller the velocity. Okay, hope we are together. For more information, you can contact me on 0785 222041. Alright, guys, lastly, this one here is what we have here as our last part of the stuff here. Now we can have what we call as firearms or the cannons. In this case, the gun and the bullet will experience the same force. Acceleration of the weapon is significantly less than the bullet due to mass difference. Recoil can be reduced by increasing the mass of the weapon. Now, what happens here? We have the gun having bullets. Ne? Now, mass of the gun and the bullet, we can get it. Then the velocity of the gun and the bullet, they are all zero because it is stationary. Now, when you shoot, after shooting, we are having the bullet out and then the gun going this direction. So you see that they opposite each other. Ne? So bullet to the right, gun to the left. Okay. So what do we say here? Total momentum before equals what? Total momentum after. Then we do substitute and then do our calculation. I think we can end up with an example as well here. Okay. This question says here, define the term impulse in words. Anybody who remembers? What did we say is impulse? We said the product of the net force and the change in time over which the net force acts on the body. The diagram below shows the gun mounted on a mechanical support which is fixed to the ground. The gun is capable of firing bullets rapidly in a horizontal direction. Each bullet travels at a speed of 700 meters per second in any side direction when it leaves the gun. Take the initial velocity of the bullet before being fired as 0. I repeat, the diagram below shows a gun mounted on a mechanical support, listen here, which is fixed to the ground. The gun is capable of firing bullets rapidly in a horizontal direction. Each bullet travels at a speed of what? Of 700 meters per second in an easterly direction when it leaves the gun. Okay. They say take east as what? Take initial velocity of the bullet as 0. Ne? Okay, so we see blades are going to the east. It's the gun here. Then the mechanical support as well. And the ground here. And the ground here. Okay. Okay, they say here that what must we do? So that the gun fires 220 bullets per minute. The mass of each bullet is this one here. What must we calculate now? What must we calculate? Calculate the magnitude of the momentum of each bullet when it leaves the gun. Okay. Now, how do we find the momentum, guys? What do we say about momentum? Do you remember? So that momentum, okay, equals to mass times velocity. Now, the mass of the bullet, we know it here. It is 0,03. Are we together? What about velocity? We see it is also 700 here. So, we can get our momentum. So, our momentum will be given by what? By the mass 0,03, okay, times what? Times 700. So what do we get as final answer here? It becomes 0,03 multiplied by 700, which gives us here 21. So we have 21 kilogram meters per second. Meters per second. Then let's calculate the net average force that each bullet exerts on the gun. We're looking for the net average force that each bullet exerts on the gun. Okay, so here we decided that the gun fires these bullets per minute. Okay, so the time taken to fire one bullet is how much time? So if we have 220 bullets in 1 minute, that means in what? That is said in 1 minute, that means 60 seconds. Ne? What about the time taken for only one bullet? Ne? So one bullet is gonna be 60 seconds divided by what? Divided by the 220. Divided by what? By 220. Okay. So which gives us 0, what? Calculate again. We have 60 divided by 220. So here it gives me 0,273. 0,273. 0,273. Now, because I have the time for one bullet, and I'm looking for the average net force, I'm going to use now that I have the time for one bullet, I'm looking for the average force. So what am I gonna do? I know that the force F net, okay, the force F net equals to change in momentum divided by what? By change in time, okay? So which is the same as saying mass, okay, into V final minus what? Minus V initial divided by change in time. Okay, so here mass of the bullet we know 0,03, that is 0,03. Okay, what about final velocity? We saw it is 700 minus 0 because it was from rest, divided by change in time, which is what? 0,273. So which answer do we get here? So we have 0,03 multiplied by 700 minus 0, which is just 700 divided by what? 0,273, which gives us 76.92. So we have 76.92 newtons. Okay, and because they don't want in magnitude, but they want the force, the net average force that each bullet exerts on the gun. Okay, so where are we pushing the gun? To the west. So we say what here? We say west. We say west. Then they say here that without any further calculation, write down the net average horizontal force that the mechanical support exerts on the gun. So now the mechanical support exerts on the gun is going to be the same force here, but opposite direction. So it's also going to be 70 what? Also going to be 76.92 newtons, but now must be east because must be opposite what? Direction. Okay. Alright guys, we have to stop here. You can try out these questions here. Those are extra classes. Don't forget to connect it tonight that we can mark them. Okay, zoom them very. So try this exercise here, please. Try it out. This question 7 here. Try it out and try it out. And this exercise here. Try it out as well. Try it out. Try it out. When you are done, don't forget to inbox me on 0785 222 041. Bye bye.